Record for that long? We'll
Should-
find out, right?
Yeah. You said you'll be done around 10, is that right?
Yeah.
Okay. Could y'all just shoot me a text when it's done? I'll come back.
Is it charged?
It's fully charged.
Okay.
It should be good. Thank you.
Okay.
Here it is.
Morning. So we're told that this is a single phase transformer. We're given the parameters for the single phase transformer. Now we want to build this Y delta transformer bank to make up the three phase transformer. So first let's find the ratings. Anybody help me with the S rating?
75,000 times 3.
Yep. And then on the voltage, we can draw it out, but we can also just talk through it and see what the voltage ratio here should be. So on the delta side, if I draw a delta, that means that this connection here will be connected here on the delta, line to line. So then whatever voltage is over here will be the line to line voltage. And we have that to be 7200 volts. And then on the primary we have a Y. If I draw that out, and again if I look at where those terminals would be connected, they'll be connected like this. So this is line, neutral, line, line. So the voltage that's over here, which is 277, would be a line to neutral voltage. And of course, for the three-phase transformer, I want to express it in the V line to line, as V line to line. So I'll take the 277 multiplied by square root of 3. Does that make sense?
So it's in line and neutral because it's a single phase transformer that you're putting together as a three-phase transformer.
Yep.
Okay, so if this ratings was given as a three-phase transformer, then they would both be in line to line already.
Yep,
Okay.
yep.
Got
So if the problem said the 75 kVA, 277 to 7,200, 60 hertz, three-phase, blah, 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 then this would be line to line and this would be
Okay,
line to line.
gotcha.
Yep.
Gotcha.
And it doesn't matter their connections at that point.
It doesn't matter, yep, yep,
Gotcha.
So it's only when it's in the single phase that we need to.
Okay.
yep.
Makes sense. Okay.
And then the per phase equivalent circuit. So the per phase equivalent circuit, of course, on the diagram, mark the series linkage impedance, okay? Nominal per phase voltage. So this is, of course, where I was drawing the per phase equivalent circuit, and that's my Y equivalent. So if I want to write out what the actual nominal voltages here are, they would be the line to line. Divided by square root of 3 on both sides. Since this is a line to neutral equivalent. Then the only unknown here is this impedance. So any thoughts about what the R and X equivalent will be? On the Y equivalent,
Would they stay the same because it's Y connected on the side that they're on?
it would stay the same if these impedances were on the Y side.
Oh, okay.
But since they're on the delta side,
You divide by 3.
Oh.
yeah,
I
we'll
think
just
I'm so
divide by
used to
3.
the high side being Y.
Yep.
Okay.
So we'll just divide by 3, yeah. But if they were on the Y, if this was a Y connection, then nothing would have changed, yeah.
So how do we mark? What does it mean when it says mark it on both sides of the transformer. Does that mean like indicate what it would equal on the other side too?
On the diagram, nominal per phase voltage on both sides of the transformer. So the nominal voltage on the primary will be this.
Oh. It's not talking about the impedance. It's only talking about the voltage.
Yeah.
Oh,
Yep.
okay.
Yep. Per phase voltage.
On both. Okay, so we don't have to mark the impedance on both sides.
Yeah,
Yeah.
we don't. If we wanted to refer this to the primary, what would that be? Let's write that out.
Multiply by a squared.
So yeah, z prime will be a squared 3 plus j31, and a would be this ratio of 277 divided by 7200 square root of 3. Which is the same ratio as 277 square root of 3 by 7200, right? It's,
Yeah.
the same.
Okay.
So nominal just means what?
Nominal means the rating. So like we said here, this transformer is rated at, this is the nominal rating of the transformer. Nominal means what's written on the nameplate.
Oh,
What's the rated value. Yep.
Could you create like a short list of all the ways that the leakage loss could be expressed? Like so there's the resistance that's in series, and then there's the resistance that's in parallel, and they've been referred to quite a few terms. So it'd be good to just clarify like which refers to which.
So this could be this could be the series impedance. This could be the leakage impedance. And then let me write that out. And then typically we call this the magnetizing branch. Or we might refer it typically we call this the magnetizing branch. Of course, this is the core loss, but rarely will we only have the core loss considered without the magnetizing branch, without considering both the reactance and the resistance. So typically you'd see this be called the magnetizing branch.
Okay. And what core loss would be the in series, right?
This would be the core loss, and then of course we'll call this usually RCXM. This would be
So RC is the core loss.
Yep.
Okay.
So XM-RC is sometimes called the magnetizing branch, where IC is the core loss.
And what was the winding loss?
And then yeah, we'll call this R equivalent and X equivalent typically. We'll call this series impedance or leakage impedance. since it's impedance, that would be X equivalent and R equivalent. In reality, this is the both series or inductance, and this is copper. Copper loss or winding loss. And the arrow can be right there. Then R equivalent and X equivalent might also be split into R1, R2, and X1 and X2.
Okay, great, thank you.
And then depending on the problem, we might call this X equivalent on the secondary without the prime, or we might put it over here without the prime. Typically, when referred to the primary, it gets the prime, but it really depends on the problem statement, right? So I wouldn't, the prime really means that you've moved the impedance from one side to the other.
The last question on this practice exam is a translational machine. That's not gonna be on our.
It's not gonna be on the, yep.
Okay. Is that on the final?
No,
Okay.
no, we didn't give it enough time to.
Okay, cool. Thank you.
Could we do number 2 on this test too?
Sure.
Let's do this test.
Number 2 here.
Right.
We have a single phase distribution transformer. These are the parameters. This X equivalent over here, and then the core loss and the magnetizing inductance. There's a load connected to the high voltage. So this is the turns ratio here. So on the high voltage side, I have a load. And we have a voltage source on the low voltage side. This load consumes the rated power. This is the rated power, or nominal is another term you might see. So rated equals nominal.
When the problem's given like this, we assume that the voltages are already in line to line, right?
What's single phase?
Oh yeah, shoot, okay.
Yep.
I'm getting so confused with this. Okay.
Yep, this is a single phase, so there won't be a line to
Okay,
line. Yep.
okay.
So these are all synonyms here, rated, nominal, or full power. And that basically just means this thing right here. And at the rated voltage. So in an exam, it would be over-explained like it is here, right?
That's good.
So calculate the required input voltage.
Would that not just be 240? Or where does the 240 go? Like, where is that value apply?
So if we go down here, okay. So this is the rating of the transformer. I have a transformer. We said the way these ratings were determined for the turns ratio is I apply a certain voltage on one side and I measure the resulting voltage on the other without connecting a load. That means this branch is ignored and this branch is ignored. So basically the 240 applied here would result in 7200, meaning that this is really the turns ratio or the ratio of voltages between the primary and the secondary of the ideal transformer. So of course, as we'll see in this problem, the voltage here will be slightly higher than 7200 and the input voltage will be slightly higher than 240, but this turns ratio will always be correct. This is like a mirror basically, and the mirror has a fixed
Okay.
ratio.
So we can just use the 240 to find the turns ratio.
So we can use this to find A, yep.
Yeah, okay.
And then we can really forget about these values.
Okay. Gotcha.
So that gives me A.
Okay.
A is 240 by 7200, whatever that works out to. So in this problem, kind of what we have is we know this voltage. We can figure this current out because we're told how much power this load is consuming and at what power factor. So I can find V phasor, I phasor, and from there I can find this voltage as I times this impedance. This branch doesn't do anything in this problem. Once I know this voltage, I know this voltage by multiplying by A. So let's work a few steps out here. So the key challenge will be finding I, and S will be V times I. In this case, we have a single phase system, so I don't have to multiply by 3 here, it's just V times I, complex conjugate. V is known, and I'll take V as always the voltage that's known at the start of the problem. I'll take that as my reference phasor. So that's V, and from there I can find I. It's going to be S divided by V. S in this case is 75000. The power factor is 1, so there's so V and I of course will be in phase. So I can write that out over here directly, and I'll just take the ratio of S to V. V is 7200, so that works out to some current. From there I can find, let's call this V as we did. I'll call this V prime, and let's call this, and it's up to you what you want, and then this is Vn as defined in the problem statement. So let's find V prime. V prime will be V, right, plus Z times I. V was the 7200 plus Z was given as this value here, 9.32, 83.8. I believe I wrote that out right. Let's see. No. 9.3 plus J, 83.8, multiplied by I'll leave I as is because we didn't calculate it. And from there I can find V prime. We'll have some value. I don't want to spend time on the math here. This will just be a real number, right? It'll just be this ratio. So from there I can find V prime. It'll be some complex number with some very small phase. And then Vn will be A times V prime. A is less than 1, so this voltage will be smaller than the input. And as the result, I'll have a voltage here that's about 240, slightly larger than 240 because of this additional impedance drop that we got from the series impedance. And these will all be complex. Then finally we're asked for efficiency here. two ways to do that. One is V times I on both sides. I could find V times this I here. That'll be P in, and V times this side will be P out. So P out over P in is efficiency, right? Another way is I could find P out. I happen to already know what it is. It's 75 kW, right? And then I can add the losses. So I have I magnitude, I squared times this R here will be the loss on this resistor. And then I know V prime squared divided by RC will give me the loss over this resistor, right? So I have to be careful. Just by looking at the equivalent circuit, I can see the current flowing through this resistor is known, so that's easy enough to find. And here I've never calculated this current because I didn't need it to solve the first part, but I did find this voltage. And of course, V squared over RC will give me, in essence, this V divided by RC is the current. And then if I multiply that by, if I square that and multiply by RC, I get V squared over R, right?
So P loss is the loss from the series impedance and the parallel impedance?
Yes, yes. So all there is, basically, if I want to find the efficiency, I can take the output power and then add all the losses upstream. In this case, I have only two resistors, so that'll be the two values I need to add. If there were some additional, let's say a line here, and I want to find efficiency from source to load, if that line has a resistive component, I would essentially look at my equivalent circuit and add up all the, calculate the loss in each and every resistor.
Okay, so P in is P loss plus P out, right?
Yep.
Okay.
So for efficiency, I have P out over P in. For efficiency is P out over P out plus P loss. And then P loss will be I squared R equivalent plus V prime squared over RC. Note, I don't care about the phase here because I'm looking at this, the magnitude only.
So do we like only use RC for finding efficiency pretty much? Because it's like, it's never really gonna affect finding anything else in the circuit.
You're right. Typically that RC will, in our problems, RC will only appear when we're calculating efficiency because we're always gonna use the cantilever model.
Yeah.
So we can always get this branch out of the way so that it doesn't affect, let's say the voltage regulation calculation or this calculation of what the input voltage should be when the output is known. In those cases, this will not figure. And looking at these problems, we'll have two cases like we talked about. One is we know what the voltage is across the load. Let's find what the input voltage should be. In that case, the trick is to find the voltage drop across this branch, and I'll move this out of the way so that I don't have to worry about it. Meaning, I'll either put it here or here so that I don't need to find, I don't need to solve around this node here, right? So that's one approach. I'll know this, let me find the input voltage. The other type of problem we looked at is, okay, we know what the input voltage is, let's find what the voltage of the load would be. So again, all I have to do is find the voltage drop across this series branch here. And again, I'll move this so that it doesn't affect the calculations. The RC XM branch.
Oh, so you would you really even have to move that branch?
Not in this
It-
case, yep.
Okay.
It's already,
Because it doesn't matter if it's on the left side of the equivalent impedance. Or...
it is not, yep. Because all I care about is what is the voltage at this point such that I can find the current in this branch.
Okay.
So yes, you're absolutely right. The only situation where this branch comes into picture is when we're calculating efficiency.
Could we do a voltage regulation problem?
Sure, we can kind of expand this one to a voltage regulation.
Okay.
But before we move on, just
Yep.
one more quick question about the efficiency. When you're finding the, I guess, that loss along that RCXM, if you were to move it, I mean, I'm guessing you're calculating that current with the voltage, and then just voltage and the given impedance. Would you not get a different efficiency if you moved it, like depending on whether you considered that series loss or not?
Absolutely. So let me see if I think I got your question here. We have the cantilever model. That means this branch can be up here or it could be down here. If it's up here, the loss here will be V prime squared over RC. And that of course is different from V squared over RC.
Yes.
So I would get a slightly different answer. Either one is acceptable
Okay.
because the difference will be very, very small. It'll be a few watts difference, number one. Number two, the bulk of the losses will be here. So if I look at the efficiency number, they will be, you know, probably the same to the third digit.
Okay, great,
Yep.
thanks.
Let me see what page am I on. This page here. Let me add a page. So we want to change. Let's add. We wanted to add voltage regulation here. That's also going to be 80%. So how would we do that? Voltage regulation is the I think it's V no load minus V full load over V full load. That sounds right. So it could be full. Let me rewrite that. That's V no load minus V full load. And again, this could be called full load, rated load. There was another term that was used, rated, nominal, or full. And it basically means that the load is consuming some rated power of the system, typically the rated power of the transformer. So how do we approach this? We're basically we're trying to figure out the voltage at these terminals here, which are the output terminals of the transformer. We're trying to find this voltage here when this full load, rated or nominal load, is connected. And we want to see how much the voltage will rise or drop when we remove the load. So we already have everything set up in this problem because I've already connected the full load to the system, and I know the voltage at full load is going to be 7200 in this case, right? So let's see what happens. So my circuit is set in stone. I have V in. There's some current flowing. This is V at the load. So V full load will be 7200. What happens when I remove the load is what we want to figure out. So V.
When you remove the load and it's open circuited, or?
Yeah.
Okay.
will be 7200 volts. And then what happens when I disconnect this load here?
You just got V prime, whatever that V,
Ex-
yeah,
Exactly, yep. V prime will then become,
that,
will be reflected over here. Why? Because Vn hasn't changed, so V prime will not change. Since V prime hasn't changed and there's no current here, this voltage and this voltage will be the same.
so you just use that to.
So yep, so V no load will be V prime.
Why doesn't V prime change if we calculated V prime using the current that we found? So if the current goes away, why is it still the same?
Basically this is the transformer. I'm trying to characterize its voltage regulation, right? So how I'm gonna do that is I'm going to apply a rated load to the transformer, and I will adjust my Vn such that at that rated load, I get the rated voltage,
Oh,
the
okay.
nominal
I
voltage.
see.
Once I got that all figured out, when I remove the load without changing the input voltage, I wanna see what will happen to that output voltage. So how well the transformer regulates its voltage when loaded.
Okay, so since Vn is staying constant, we can expect the voltage on the other side to stay
Yep.
constant like right? Okay,
Yep,
that
yep.
makes sense. Thank
So
you.
we will not be changing V in between the two experiments, between the full load and the no load experiment. Yep. All right, anything else on this one? Or anything else, or what do we wanna talk about next, I guess?
I had a quick question.
Yep.
In class, we went over like a few buck auto transformers. Could you show an example of a boost one, like what the connections would look like?
Sure, let's do that. Just stay on this file here. Since I'll post this, I'll just say not on exam. And then I'll add another page here. So we'll have a transformer that looks like this. And let's make this, for example, 120 to 12 volts. So basically what we want to do in these kinds of problems is put our two windings in series. And then in a practical scenario, the buck boost will increase or decrease the voltage by a small amount. So 120 is the nominal, and now I'm getting to 132. So this would be this would typically be the boost case where
Where's the output for the second one?
so the way we drew this, we could say how I would use this in a real circuit is I would have V in here, and this would be V out. In practice, this V in would be, I'd have a line that's running high, and then V out would be bucked or reduced to the nominal value using this buck boost. So the power flow would be like this would be that same current here. And then current would be coming out here. And I have the two currents subtracting here in this main branch. So if I make this a 1200 VA transformer, then this current here would be 10 amps. This current here would be 100 amps. Sorry. This current here would be 10 amps. And then if I look at this node here, that would make this current 110 amps. So this is the so if I look here, 100 amps goes in, 100 amp is coming out, 110 goes in, 110 goes out. That all makes sense. And if I look at this node, 100 sorry. This is 10 amps. I'll move this arrow, that's the confusion here. I'll move it down here. So 100, 100. This is an ideal transformer. So if I have 100 amps here at 12 volts, I must have 10 amps at 120 volts for the transformer to be processing 1200 VA at any time, right? Because 120 times 10 is this number, and then the same thing is going on here. So that ideal transformer is still behaving as expected. But then if I look at this node, as these two currents come together, they must come out this way, and it'll be the sum of the two. So that's how I end up with, you know, the output rating of 1200 times 110, which is, you know, over 12, over 120, or sorry, over 12,000 VA versus 1,200 VA. So this looks exactly the same regardless of if this is a buck or a boost. The only difference is if I drew the buck, had I drawn the boost, all these currents would just change direction. So this would be going in, this would be going down, this would be going up. But all the values would stay the same.
And you would say V out is on the side where V in is.
And I would flip, yep, the input and the output. So this is completely bidirectional.
Okay.
Can you show how that relates to the top circuit? Like how you would connect it and where the currents would be going? Because that's what's confusing to me, is to like relate the two.
Let's see, I have a really nice Visio file that I was looking at just yesterday that I'll post, but let's work it out over here too. So So let's make this terminal here, terminal A. That's current flowing into the 12 volts. So I'll make this terminal A. It flows into the winding here, and I get to this midpoint, and then let me see if I look at this 120 here, and current, let me find the terminal that the current is flowing out of, so this terminal here should be this terminal here, so let me call this B, this must be B, this must be B, so this guy and this guy need to be connected like this. And then on the other side of this transformer, I must have C. So C is goes one way over here and goes the other way to the output. So this is my negative, and this will be my negative on the other side. And then if I go all the way back up to A, this will be the positive of, I'll put it out here so that they are looking the same. So this will be V in. And then on the output side, I am going between B and A. Between C and A. So C is my negative, and I'll take B as my positive here. This is V out. So if I follow this diagram here, the positive of the B is actually connected to 120. The negative is connected to 120, so this 120 is here, that worked out. And then if I look at the V in, it's going to have these two windings in series. Let's look at that. If I start from the positive, I have this winding, then I have this winding, and out it goes. So the easiest thing is draw what you need, and then find the relation between the two that way. Yep.
The polarity of the inductors, like the dots you draw based on where the current goes, it's you draw the dot on the side where the current goes in, right?
Yeah, so we should put the dots here and here, and that would put the dot here,
So it's on the input side?
and let's find where C is. Sorry, let's see. So this is 120 here. On the 120, I will put, okay, I got the 120 here. The dot should be at the C. The dot should be at the C, so I should put the dot here, okay? And then if I look over here, on this one, if this is A, I shouldn't put the dot at A. I should put the dot on the other end, so over here. So this, we know, right? We know that for our ideal transformer, we want the current going into the dot and coming out the dot on the other end. That way I know the MMFs, magnetomotive forces are opposing. The big F's are opposing, otherwise I'm just gonna saturate this guy. So I want the MMFs opposing. For the transformer, the notation we like to use is current flowing into the dot on one side and coming out the dot on the other. So once I've drawn that, then I can map that down to the other transformer.
Okay, thank you.
Yep, so here current is going into the dot on the 120 side, and current is going out of the dot on the low voltage side.
Could we do some nasty magnetics problems? Like, yeah.
Oops.
Yeah, like a circuit that would make half the class cry.
I won't do that to you guys on the exam.
75%.
Little hint there, but be happy to do a problem like that. So we could just make one up, or we could do an exam problem.
I don't have any particular exam problem in mind. I haven't looked at them yet.
This one isn't terrible.
I found one on fall 2016, exam 1, number 3.
Now I gotta study for 302.
And the 302 homework.
And the 302
Oh, I'm skipping the 302 homework.
I already
That's
skipped
so
one,
smart.
so I.
Oh, the
What-
302
what
lab is
class do you
easy.
want? Is
It was easy, but it was just
It
another
took
thing
like
I
20
had to do
minutes.
in my
Yeah.
week.
Yeah.
Today?
The post lab's not too bad either. The
Yeah, I
post-
did the
Okay.
post lab.
It just is a
Oh,
little.
that's really good to know.
Yeah. kinda.
But you don't have to like write out the introduction and all that.
Just like answer questions.
The lab is so quick though.
Leo was, took that with Michael and Sean.
Was it this one?
Yeah.
That's what we're taking now, yeah.
That's it, yeah.
The top one, this one here.
Number 3, yes.
Like, I got
You?
out- there's the same one. I got
I
out,
took all that
like,
in
a little after
the
I
last
got
3
here
days.
about 6
It was crazy. Yeah.
All right, let's look at this one here. I have a magnetic circuit.
Yeah, or it was maybe closer to 6. But
I got
still,
100
it was
turns.
like 8 miles, so.
Permeability is given.
What question?
We got mu naught. Material cross-sectional area is 2 centimeters, and then the core length is 20 centimeters. And we need to find we need to design an inductor of 5 millihenries. In other words, by changing this gap. Don't worry about, here it says mean core length is 20 centimeters. Don't worry about the error of the air gap here. You're given that it's 20 centimeters, and that's the number we'll use regardless of what value we get here. We don't need to subtract out G in our calculations, right? The reason is we'll find that G is probably usually in the millimeter range, right? So if I take a millimeter out of the 20 centimeters, it won't change the result a whole lot. So the mean core length, and again, it's not a very precise measurement to begin with, just stick to the number that you're given in the problem. And that's actually reasonable in practice as well. As we saw, basically that core is what it is. We can't change its mean core length. Okay, in other words, in the real case, what we had was, we had a U core here, or an E core, and basically this mean length would not change regardless of how we space the gap. And we know that regardless of if I have an E core or a U core, basically this G can be converted into a single gap rather than having the 3 little ones that once I know what the total gap is, I can just divide it by 3 for an E core or 2 for a U core. Okay, required gap size to get the inductance. So in this particular circuit, I can use my equation that L is N squared over the reluctance, because I have, that's always true, right? The tricky part is, you know, what reluctance should I be using? In this case, since I have only one winding, and I'm looking for the self-inductance, which is the inductor value, right? This will be the equivalent reluctance seen by when this winding tries to inject a flux in this system, right? So my equivalent circuit looks like this. Always good to draw it out. This is our gap, call it, this is our core, this is my N times I, and this will be the flux. So I could write lambda 1 is n times the flux, which is n times, this flux will be n I over R total. R total is RC plus RG, right? The total flux in this simple circuit, I only have one path. So that's L11. So L11 will be n squared I over R total. And then L11 is n squared over R total. So that's where we got this formula, right? But we can take that shortcut. What this tells me is this reluctance will be the reluctance seen by this voltage source when it tries to induce a flux in the circuit, right? So in this case, that's all super simple because there's no multiple paths in the system.
Can we expect one on the exam that does have multiple paths, or would they be like this?
Well, let's do that. Let's say we have, let's do this one and then we'll try a different example that's a little bit more involved. So here I have L is n squared over R total. N is known, obviously, I'm given 100 turns. L is known, I know what inductance I want. So I know what R total I need, total reluctance I need, should be. And I'll just add a page here. So we don't have to go back and forth. This is that equivalent circuit. R, G, RC, and I. And then we said L is n squared over R total. And then R total will be n squared over L, and that's known. So R total is known now, and it'll be equal to RG plus RC. RC is L by mu naught mu A, right? And RG is G over mu naught A. So RC is the core reluctance. This will be that given length of 20 centimeters. We know mu naught, mu is 1200, and the area is known, right? So I can find RC. For RG, mu naught is known, the area is the same, but the gap is unknown. So I can calculate this gap based on this algebraic equation, right? Yep.
In the problem statement, when it says that mu is equal to 1200 mu naught,
Yep.
is that encapsulating all of mu, or is that the, like, do we still have to multiply by another mu naught, or is that like everything we need?
So we have mu is mu r times mu naught. And in our case, we're given that this mu is basically 1200 times mu
Okay.
naught.
So we don't have to multiply by another mu naught.
No, so we're given the material property, which is this mu is mu relative, 1200 times mu naught. So, yeah, this will be the 1200 mu naught, A, L, done. This is the 4 pi 7, 10 to the minus 7. A is known, we can find the G. So that's important point here, just be careful, and that's a bit of a pain, is this is in centimeters, right? So make sure you convert that into meters. So this would be, that one way to do it is AC could be 0.002 meters. That's 2 centimeters, right? No, that's 2 millimeters. So
You need one more zero.
let's see, centimeters, decimeters, meters. So this is 0.2 meters. The way I like to do this, times, and we're right here. AC is 0.02 meters times 1 centimeter, 0.01 meters. So that'll give me the correct value. So I'm multiplying a centimeter by 2 centimeters, that'll give me 2 centimeters squared. But I just expressed the 2 centimeters and 1 centimeter in meters. It's a bit of a pain, but be careful about that. And then this is easier, the LF is given already is 20 centimeters, so you don't have to do the square. It'll just be 0.2 meters, right? 20 centimeters, 200 centimeters would be 2 meters, so 20 is 22. Okay, so that's that. And then if the magnetic circuit is excited by 1 amp, find the maximum flux density in the core. Okay? Assume that the flux density through the magnetic core and the gap is uniform and the fringing can be ignored. We already did that because we used AC everywhere. This A didn't change, meaning the fringing is ignored.
Is it
Okay.
ever gonna tell us to not ignore that?
It's not,
Okay.
yeah. Not in any other problems we looked at.
Okay.
So I want to find the flux density. So if I look at my equivalent circuit, this is that flux. I only have one flux in the whole circuit, right? Because I don't have multiple paths. So once I find the flux, I can easily find the flux density. So flux is Ni by Rc plus Rg. I already know, I've calculated these values. In fact, I can do it right away. I know it's R total. So Ni divided by R total will be the flux. I'll write it down here. Flux is F over Rc plus Rg. And then I in this case was given as 1 amp. Okay, this is a tricky one. I wouldn't do that to you guys, but so that's the flux, and then B will be flux divided by area, flux density, right? So I can find what that is. Now the tricky part here is I'm told if the magnetic circuit is excited with a current of 1 amp, RMS is the key word. So this is if this magnetic circuit is excited by AC current, which is reasonable. If I have an inductor, of course I'm going to excite the inductor with AC current. Find the maximum flux density in the core. So since it's an AC current, the flux will be at its maximum when the current is at its peak. So I shouldn't be using 1 amp, right? In other words, this is generally true. This statement is true. And then at the end we can do, oops. At the end we'll do this at the bottom. But what this problem says is, actually, if I want to find the flux, it'll actually be a function of time, because I is an RMS value. It's 1 amp RMS, which is 1. That's the root mean squared value multiplied by square root of 2, multiplied by whatever cosine or sine some omega t. And I don't care what omega is, because if I was able to find the root mean square value, I don't care about the frequency, I know what the peak magnitude would be. So flux max will, when omega t equals to 1, right? Sorry, 0, right? When cosine of 0 is 1. So F max will be n times square root of 2 over R total. And then easily enough you can find the flux density by dividing by the area. So yeah, the tricky part here is, maximum flux density. You have to recognize that that current is a RMS value.
So is that max when cosine is 1?
Well, cosine is 1, yep. So let's look at a crazier magnetic circuit. Let's say we get something like this. Let's say we got something like this. So let's say we have a magnetic circuit like this, and I have a winding here, and let's put another winding over here. So let's say I want to find again just the inductance of this winding 1. So I could call that inductance, or the correct term would be self-inductance. L11. So in that case, as always, the first thing is let's draw the equivalent circuit. So we'll have some resistance here, or a reluctance. I'd have to split up this circuit here, call this R1. Then, actually I can't even do that. And then let's have another one here. That's how I would split up these resistors or reluctances. I'll call this R4. And then finally, this R5. So I'll split this up in a way where in this branch here, this reluctance, and this reluctance are all in series. So I can just sum up the total length, assuming the cross-sectional area is the same. So reluctance will be L, the sum of these three, divided by mu naught, mu r, multiplied by the cross-sectional area of all these components. Now in this branch, I have this reluctance, and this reluctance all in series. So I can combine these two, assuming same cross-sectional area and same material here and here. Then this reluctance will be L1 plus L2 divided by the area and then multiplied by mu naught mu r. And then I have this R3 over here. And similarly this and this can be summed up as R4. And then I have the R5. So that's the equivalent circuit. What does L11 represent? L11 is lambda 11 divided by I1, which is N1 flux 1 divided by I1. This is Ni1. This is flux 1. And then if I keep going here, I get N1. And then this flux is a little bit tricky, so I gotta go in and find what that is. So this flux will be of course, Ni1 divided by the reluctance, which will be R1 plus R2, R3 in parallel with R4, R5. Yep.
Why did you not include the air resistance, air gap?
Which one? This one here is R5,
Oh,
this one here is R3, and then R4, I summed up this one and this one.
I see.
And then for some reason we didn't have one here,
Makes sense. Thank
just to make it a little bit easier. So, okay, that's the flux, and then yeah, we said the equivalent reluctance will be R1 plus R2, R3 in parallel with, or whatever that ends up being. So then I'll have N1 squared divided by the appropriate reluctance, which in this case is a little bit more nuanced than in this case where we only had one path for the flux. So I can do the same for the other winding. Same definition, L22 over I2 and 2 flex 2 over I2, and again, the tricky part is finding flex 2. So in this case, I'm going to have the MMF here, and I want to find the current, or sorry, the flux through that MMF in this branch. So that'll be R5 plus R4, and then these would be in parallel. So it'll be R5 plus R4 plus R2 plus R3 in parallel with R1. Sorry, that's the flux. Sorry, that's the reluctance. I still need to divide by Ni. Right. So how did I get this? Let me draw it out. So in this case, the new circuit would look like this. So R5, R4, R2, R3, R1. And finally, if I wanted to find the mutual inductance, I could excite N2, I2, and I would want to find the flux here in this branch. Should we do that as well?
Yeah.
So L12 will be lambda 12 divided by so let me copy this here. Apparently I don't know how to copy, so we'll draw it out. Before we start that, let's draw out what we're trying to find. So we could do this either way, we'll get the same result. L12 and L21 are the same. So let's, for example, leave that source over here. But the flux I'm looking for will be this flux here through coil 1. So L and let's say this I want N1, oops, be N1 times the flux divided by I2. And call this flux 1. And this will be the plus, that's why I gave F1 the direction I did. So again, I can find that flux. It's a little bit more complicated. Let's not do the, circuit analysis here. But for example, I can find this current here and then do the current, I could find the current here and then this current will split two ways based on the impedances, so there's a formula for that. Another way I could do this is I could find this current here. Once I know this current, this voltage minus the voltage drop across this branch here will give me this voltage divided by this resistance gives me this current, or this MMF divided by this reluctance gives me this flux. That's the way I would probably do it. So, excuse me.
Let's see.
Thank you. So we can find F1, right? Is there any need to do that? Okay, then we'll just say F1 is basically is going to be N2I2 divided by some R equivalent that we don't want to bother finding. And then if we plug that all in, of course you'll see that L12 will be N1, N2 multiplied by I2, I2's cancel out, divided by R equivalent. So again, L12 will be N1, N2 divided by the reluctance. The point here being that this reluctance, if I have a complicated circuit, it may not be that obvious what reluctance I'm using. In the case of a single path, like we had all the way up here, case of a single path, it'll always be R total, right? Both for L11, it'll be N squared R total. L22 will be N2 squared over R total. And then L12 will be N1, N2 over R total. So that's the formula we have in the cheat sheet. But you have to, of course, be careful about using the correct R total. And to figure out what the correct R total is, the best way is, to go back to the definition of inductance. So, since I'll give you all a hint here, you're not going to get a complicated magnetic circuit on the exam because it'll take, as you can see, more time than we have on the exam. So.
Any other tips?
So just fundamentals. Always think about the fundamentals. The point is not to be. I want you, of course, to do this on the homework and think about this and understand this. But on the exam, we want to kind of stick to the fundamentals and higher level conceptual issues like, basically, for example, what we did in our term project, we looked at how do you find the inductance, right? This is a reasonable problem. And then, for example, how you would figure out what is the maximum current that you can get out of the magnetic circuit before saturation. I think this problem is reasonable, so this problem 3 would be a reasonable one to have on the exam. Some of these are a little crazier. This is also reasonable, right? Because I have, so make sure you can do this, right? Type of problem. So here we found the self and mutual inductances, but I only have one path, so it's feasible to solve in an exam environment. And then for a transformer, where do we put a dot here? This is an easy one we can do in a few seconds. Red will be on the top because I want my MMFs to oppose as they do in this figure with the current directions shown. So right hand rule says MMF up, and the right hand rule here says MMF is also up, so the MMFs are opposing.
Wait, wouldn't it wrap around like Oh, because it comes out the back.
Yeah.
Okay, yeah.
So it comes out here, and then this guy comes out.
Yeah,
here.
okay. Gotcha.
So the equivalent circuit would be this one.
He should post that in like the student, in like one of the forums on the Moodle.
Yeah. I
Cause
texted him.
if it gets sent to my phone, I think my phone will blow up.
I don't think it will.
Storage.
I saw the thing that was like, we're sending people to the moon, but I can't send this big of a file.
Yeah, right.
What is going on?
My phone,
I tried to
think
send
my
like
phone
files
would
to myself,
display.
like too big to be like, what do you mean?
Yeah, so
That is gonna be insane.
if you could just post that.
All right, any final questions or anything else, let me know. There'll be office hours on Monday as well with the TA. And then shoot me an email if you have any questions.
Thank you.
Thank you.
Yep,
Thank you.
no problem. I'll post both these, I don't know how helpful that will be, but these notes, these annotations we did, I'll put that up on the site.
Thank you.
Yep.